Exercise 4. Develop a math model for the following problem. If the model is a linear programming problem, solve it manually and interpret the solution. A staff dietitian is planning a lunch for a children's summer camp. She believes a turkey and cheese sandwich would be good. Both the turkey and the cheese are purchased as large rectangular blocks, with cross-sections of 3.5 inches by 3.5 inches. The thickness of the slice is determined by adjusting the thickness gauge on the deli slicer. Any thickness up to 1 inch is possible. It is the thickness of the slices that the dietitian must determine. In order to be tasted, both the turkey slice and the cheese slice should be at least 50 thousandths of an inch thick. The turkey and cheese combined is to provide at least 200 calories and at least 10 grams of protein. The turkey and cheese combined should have no more than 600 milligrams of sodium. Nutrition fact labels of each are provided. Also, the cost of a 100 thousandths inch thick of slice of turkey is 50 cents, while a 100 thousandths inch thick slice of cheese costs 30 cents. At what thickness should the turkey be sliced, and at what thickness should the cheese be sliced, so that all the requirements are satisfied and the lowest possible cost is incurred? Record at least 2 significant digits for all numbers. Where to begin? Notice the variables here are going to involve the turkey and the cheese, but what about them really? If you take a look at the available information, this nutrition fact label, as far as the basis of this, you see the entire label versus the turkey label. The entire label is based on amount per serving. The serving sort of defines the basis for all the information that you provided. And the same is true for the cheese, and in fact, all nutrition fact labels are like this. First they define what a serving is, and then all the information is based on that. Well, that being the case, it might do us well to actually bring in as variables. For instance, X might be the number of servings of turkey, and Y might be the number of servings of cheese. This way, the formulation will probably be easiest. Of course, there are other ways to formulate a math problem. There's no strict rules, but this might be a pretty good idea here. So let's try that. Okay, let's let X equal number of servings of turkey. And similarly, Y could equal, ditto quotations here, number of servings of cheese. Okay, now the key quantity here, we're trying to get things done here at a minimal cost, so we could perhaps let C equal the cost of turkey and cheese. And let's see if we can formulate that right now. We did say that we were going to let X and Y be the number of servings of turkey and cheese respectively. The cost information available to us here says up here, the cost of a 100 thousandths inch thick slice of turkey is 50 cents, while a 100 thousandths inch thick slice of cheese costs 30 thousandths. Okay, let's see if we can't get this in terms of servings. Let's go back, look at that. Okay, in the case of the turkey, a serving size here happens to be a slice 100 thousandths by 3.5 inch by 3.5 inch. Okay, very good. That happens to match up exactly with the cost that has been described. Alright, and as far as the cheese goes, its serving size is also 100 thousandths by 3.5 inches by 3.5 inches. Okay, that allows for a very easy adaptation of the cost information provided to writing a cost formulation. Here's what we can do. C would equal, okay, in this case, what we have sitting here, the 50 cents corresponds to 1 serving. So if we have X servings, we're going to get 0.50x plus, and in the case of the cheese, what was described here, this 100,000 inch thick slice of cheese happens to be one serving exactly. That's 30 cents on a serving. So then that allows us to write 0.30 times the number of servings, y, to get the cost of the cheese. Okay, so there we are with this cost function formulated. We are trying to minimize. Again, this is we could call this the objective function. Okay, now let's see. What about the domain? Subject to. What are our concerns? Okay, always got physical sense in a real problem, it seems. So let's talk about that. First at bat, physical sense. What about that? We're talking about number of servings of turkey and number of servings of cheese. You can't have a negative number of servings, so right away we have x greater than or equal to 0 and y greater than or equal to 0. Okay, now let's start looking back at the problem and see what else we are concerned with. Let's see. Here's the first item that looks like it's going to dictate x and y, what's allowable. In order to be tasted, both the turkey slice and the cheese slice should be at least 50 thousandths inch thick. Okay, we can formulate that too. Remember one serving? It was 100 thousandths. If we're going to require 50 thousandths, this is actually requiring a 1/2 serving. So, here, minimal slice thickness, we would have this saying then that x is greater than or equal to 1/2 and y is greater than or equal to 1/2. You notice now, these restrictions have sort of overwhelmed these first two as far as our future domain goes, but okay, that's right. They were sort of two separate considerations, and now we've got them. Let's see what else we can say here. The turkey and cheese combined is to provide at least 200 calories. Okay, so provide at least 200 calories. Okay, what do we do here? We need to go and consult that nutritional fact label again. Okay, nutritional fact labels always tell us how many calories are in a serving. In the case of the turkey, it looks like one serving provides 50 calories. In the case of the cheese, looks like one serving provides 100 calories. Okay, this means the translation of this requirement would be that 50 calories per serving of turkey times x servings plus 100 calories per serving of cheese times y servings has got to be greater than or equal to, remember, at least 200 here. Okay, I guess kind of keeping organized here, let's say here's inequalities 1. Here we're inequality pair 2. Here is inequality 3. And you probably would like to simplify this one right away. It looks like both sides divide by 50, actually. That would be kind of nice. And if we do that, we could rewrite this as just x plus 2y greater than or equal to 4. This could be 3a. Okay. Alright, so we've got the calorie requirement in order. Let's see what else we have to be concerned with here. So the turkey and cheese combined is to provide at least 200 calories and at least 10 grams of protein. Okay, there's something. So here, provide at least 10 grams of protein. Alright, what about that? Well, we need to take a look at that nutritional fact label again for the turkey. There we are. The protein requirement, protein content rather, is down there. For one serving, it's 4 grams. for the cheese, the protein requirement, also 4 grams. A coincidence. Alright, just the kind of information we need though. So 4 grams per serving turkey, 4 grams protein per serving cheese. This allows us to go ahead and formulate this as 4x plus 4y. Okay, at least 10 grams. It's got to be greater than or equal to 10. Okay, there's inequality 4. Let's see. Both sides divide evenly by 2. So we could rewrite this as 2x plus 2y greater than or equal to 5. Call that 4a. Alright, let's see. What else do we have to worry about here? The turkey and cheese combined should have no more than 600 milligrams of sodium. Okay, you got to watch out for that sodium, right? Hypertension, get too much sodium in your system. So this is good that we're concerned about this. And let's try to translate this. First, what is it? We have here contains no more than 600 milligrams of sodium. Okay, we need to go back to that nutrition fact label. Take a look at for the sodium contents of these. In the case of the turkey, one serving of turkey's got 300 milligrams of sodium. In the case of the cheese, one serving of cheese has got 180 milligrams of sodium. Okay, that gives us just what we need to formulate. Okay, so we have 300x plus 180y. Now, no more than, so that means it's less than or equal to 600. Okay, this could be inequality 5. Both sides divide by 10 evenly. More than that, actually 60. Divide both sides by 60. Okay, and then that would give us, let's see then, 5x plus 3y less than or equal to 10. Okay, inequality 5a. Alright, anything else? Okay, we got up to here the sodium. Fact labels are provided. This talks about cost. That doesn't control the domain at all. What thickness? There's the question. Okay, so here's our math model here. We've got it right before us. What do we think? Alright, minimizing cost. It's an optimization question. Here's the formulation of the cost function. It's linear. Okay, now let's look at the domain. How about that? The domain is being defined by a system of linear, 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 linear inequalities. Okay, this is indeed a linear programming problem. Okay, so this means we would do real well to sketch the domain or the feasible region and find the vertices, and then we'll calculate the cost at each vertex and be able to make a conclusion. Okay, let's get on to the graphing of the feasible region next. Okay, to begin this graph, I want to think about what kind of coordinate system is set up to make the feasible region fit. Okay, so this x greater than or equal to 0, y greater than or equal to 0. Okay, that puts us in the first quadrant. This one here, x greater than or equal to 1/2, y greater than or equal to 1/2. Okay, this puts us a little further into the first quadrant. Now this one, I would like to imagine graphing the boundary line to this, and that means I'd like to see some intercepts. When we let x be 0, y will be 2. When y is 0, x will be 4. Okay, 2 and 4. This one, when we graph the boundary line, I'm going to be wanting to get the intercepts. At least I'd like to. So I consider x be 0, y is 2.5. Y is 0, x is 2.5. Okay. This third one, when we graph the boundary line, in other words, this becomes an equality for a moment. I'll let x be 0, y is 10/3, okay, 3 1/3. When y is 0, x is 2. Okay, looks like everything here, rather small numbers between 0 to 4, looks like it would fit everything pretty nicely. I like to put the coordinate axes in here, so I always tend to go to x and y down to 0, no matter what the problem. So let's try going with, let's see, to make this fit and be as big as possible here. How about a half serving per centimeter scale? Okay, so here would be x, and in an application problem, it's actually really better to label your axes with physically what is going on here instead of the algebraic symbol. And we will recall our definition. This is the number of servings of turkey. And here on this y-axis in algebra, but in words, this is the number of servings of cheese. Okay, for some scaling, we said a half serving per tick mark, so 1, 2, 3, 4 there, and 1, 2, 3, 4 there. Alright, time to take out our first contrasting color. Now the first quad, x greater than or equal to 0, y greater than or equal to 0. Okay, that puts us on this coordinate system basically. Now let's go to here, x greater than or equal to 1/2 and y greater than or equal to 1/2. Okay, now the boundary line in the first case is a vertical line, x equal to 1/2. Okay, right there, 1/2, and the equation. Alright, and then we are to be greater than, we're over here to the right of that. I kind of mentally keep track of that. The other one, the boundary line is the y equal to 1/2. That's a horizontal line. Okay, about like so. The equation here, y equal to 1/2. Alright, so now we know we're in here as we proceed further. Now, let's take out another contrasting color. Let's go to, this is our next one here. We choose the 3A version. Okay, the boundary line in this case, okay, let's see, let's let x be 0, y is 2. Let y be 0, x is 4. Okay, the straight and solid line to connect these points gives us our boundary line. Label its equation here. This was the x plus 2y equals 4. Now, which side of the line are we to be shading here in this case? Okay, if we test 0, 0 here, that makes this false. Okay, so it's not 0, 0 side of the line, it's the side away from 0, 0 that gets the shading. So far we are this direction of the blue lines, and now we are this side of this red line, bringing us to this intersection so far. Okay, time for another contrasting color, and let's go to the protein restriction here. Okay, 4A is the best form for us, and the graphing of the boundary line. Imagine this is an equality for a minute. let's get the intercepts of that boundary line. Y is 0, x will be 5/2, 2.5. If x is 0, y is also 5/2, 2.5. Okay, so intercept there, intercept there, and when I have them right on the tick marks, I label the tick mark. This is 5/2, this is 5/2. Okay. The boundary line, solid line, right? Because it's an or equals to type of inequality. Which side of the line gets the shading on this case? Okay, it's a let's test 0, 0 here. If we put 0, 0 into this, 0 greater than or equal to 5, that's false. Okay, so we're to the other side of the line. Now that means this side of the green line, and we have to keep intersecting with what has previously been sketched. What that basically does is, here was the intersection. Now this green line comes in and pushes us forward a bit, so it doesn't make too much difference like here or over here, but right in here, the green line is now forcing us forward of here. No longer are we allowed to come back to this red or blue line in this little zone here. Okay, so we kind of keep track as we go. And we should label this green line with its equation. Right here, their boundary line has got the equation 2x plus 2y equals 5. Okay, let's go on to the last inequality, 5a. The sodium restriction. Okay, now if we sketch the boundary line here, imagine this to be an equality for a minute. If x is 0, y is 10/3, 3 1/3. Okay, let's get that now. Here's 3, there's 3.5, 3.3 about there. Now that is actually 10/3. Okay, if we come back here, let y be 0, x is 2. Okay, right there. Okay, another boundary line. Okay, now, which side of, well, let's label its equation. Okay, the boundary line here has got the equation 5x plus 3y equals 10. Now, the shading. If we put 0, 0 into here, that gives us 0 less than 10, which is true. Okay, so now we need to shade the 0, 0 side of the purple line. Okay, so be a little careful here. The domain prior to the purple line was everything forward of all these lines here. Now the purple line comes in and it is to be shaded to this side. If we want the overall intersection of this, we need to stay forward of the blue, or maybe I'll say to the right of the blue, the green, and even this little red here, and the origin side of the purple. Okay, I'm going to shade this with the pencil. It's a rather small domain resulting here, or feasible region. I use pencil gray to shade this one. Okay, I want to label that. Try to use the same color. Feasible region. Okay, now as I look at this, I do notice 4 vertices. Okay, I like to make those clear. Okay, now there's one here. I like to make it more prominent so someone reading the solution can have these important vertices really stand out. Okay, one there. careful here. There's a little red line boundary that bounds this. This is a quadrilateral shape here, right? Here's another vertex right there. And lastly, over here, another vertex. Okay, now we can start computing these coordinates of these vertices here. This one, okay, let's see here. Now this is fairly simple to compute because it's the intersection of the blue line, whose equation is really simple, x equals to 1/2. Okay, and then the purple line, whose equation is 5x plus 3y equals 10. Alright, so maybe right here we can just do our scratch trick right next to this. X has to be 1/2, so we would have 5 by 1/2 plus 3y equaling 10. Okay, so this is 2.5. Subtract from both sides. 7.5 here. Maybe fractions is nicest, so 3y equals 7.5, which is also known as 15/2. So then y would equal, divide both sides by 3. 3 divides the 15 evenly. 5/2. Now, let's make sure that this makes graphic sense, otherwise we made a mistake. Again, always try to do little checks as you go. Look for the consistency, because one mistake in the middle of the problem can ruin the entire problem. Alright, so how about this? Look at the graph. Here's our y. 5/2 looks quite good, actually. Okay, so we'll keep this coordinate. 1/2, 5/2. Okay, got that one. Let's see, another one that looks fairly easy to compute would be right here. Now, x has to be 1/2 because it's on the blue line, but it's intersecting the green line. Okay, so, alright, we know 1/2, and we have to figure this out. Let's go to the green line, substitute in 1/2 for x, 2 times 1/2 plus 2y equals 5. So that's just 1. Subtract 1 from both sides. 2y is 4. So then y would be equal to 2. How about graphic sense? Yeah, there's a y coordinate of about 2. Looks pretty good. Alright, got that. Now, here, what about this one? Alright, maybe an actual subcalculation off to the side. Put an asterisk. Refer the person reading this up here to see where this will come from. It's the green line and red line intersecting. Green line and red line. Okay, the green line, 2x plus 2y equals 5. The red line, here, x plus 2y equals 4. Okay, we've got to figure out the solution to this system. No problem. This thing's ready for a nice elimination. We could take the first equation, subtract the second from it. That'll eliminate the y's immediately. Okay, 2x minus an x. Just x. 5 minus 4. That's 1. Okay, make sure it's okay here. Let's look for some graphic consistency. X equal to 1. Does that look okay? Here's the point down here. Yeah, that looks pretty good. Okay, and then to get the corresponding y, recycle this second equation perhaps. You'd have 2y equals 4 minus x is now 1. So there's 3. That would give us y equals 3/2. Do we like that? Look for graphic consistency. Here. Here's 1, there's 2, there's 1.5. It looks pretty good. Okay. 1, 3/2. Okay, here. Another vertex. This will be a subcalculation, 2 asterisks over here. Okay, what's going on in this point? It's an intersection of the purple line and the red line. Okay, purple line, 5x plus 3y equals 10. And red line, x plus 2y equals 4. Okay, gotta solve this system here. Let's see. We could set up an elimination of y's. What if we just do 5x minus 5 of these? Is that too brutal? No, that doesn't look so bad. Okay, we'll just try that. It gives us an immediate results this way. So first equation, minus 5 of the second, will eliminate the x's. 5x minus 5x. X's are gone. 3y minus 5 times 2y to minus 10y, negative 7y. Okay, 10 minus 5 times 4. That's 10 minus 20, negative 10. Okay, this leads us then to y equals, okay, negative divided by a negative is a positive, so we're sitting here at 10 sevenths. 10 sevenths, that's like 1.4. How's that look graphically? Looks pretty good. There's 1, there's 2, there's 1.5. Okay, we seem to be on target here. Keep going. Get the x. Recycle the second equation as the source. X would be 4 minus 2 times 10 sevenths. Okay, looks like we are going to need to be in the realm of sevenths here. So 4 would be 28 sevenths. Minus, here's 20 sevenths. Bringing us down to 8 sevenths. Okay, 8 sevenths, that's like 1.14. How does that look graphically? Okay, yeah, there's 1, there's 1.5. Well, it looks pretty good. Let's keep this. So this gives us the point whose overall coordinates are 8 sevenths, 10 sevenths. Okay, we've got our feasible region, we have all the vertices, we're ready for the next phase, which is to calculate the cost function at each vertex, and then we'd have our conclusion. Alright, so ready to form our table of evaluation. First column will be the vertex. Here we can put our cost. C equal to, okay, go back to our original formulation of this problem where we had found that the cost function was 0.50x plus 0.30y. You know what? Now that I see this, I think we might do better off in terms of fractions here. So C equals, let's see, 0.5 easily written as 1/2 x plus 0.3, okay, 3/10 y. Just because of the nature of our vertices, they seem to have fractions, and it's easier to work with that manually than with decimals. Okay, so let's get started. I guess we could start here and move around in the counterclockwise direction. So 1/2 5/2, and 1/2 2. Then there's this 1 3/2, and then there's the 8 sevenths 10 sevenths. Okay. Alright, let's get started here. This first one, we get 1/2 times 1/2 plus 3/10 times 5/2. Okay, cancel 2. This is a 1/4 plus 3/4. Okay, that equals 1. Exactly 1. Okay, here. This is 1/2 times 1/2 plus 3/10 times 2. Okay, so we're looking at 1/4. Cancels 5. 3/5. Okay, we need to go to 20ths, right? Okay, 5/5 build up here. 5/20 plus 4/4 build up here. 12/20 equaling 17/20. Okay, now let's see here. This would give us 1/2 times 1 plus 3/10 times 3/2. This is 1/2 plus 9/20ths. Okay, we're in 20ths, then we'd have a 10/20ths here, and 9 more, that's 19/20ths. Okay, this one here, we got ourselves 1/2 times 8/7 plus 3/10 times 10/7. Okay, cancel 4 here. 4/7 plus cancel 3/7. Okay, 7/7 known as 1. Alright, well, we're trying to find the minimal cost. Okay, right here, by the way, a 20th, that's 0.05 each, right? So actually, we have here 1.00, 17/20ths. Okay, you can say 0.85. You can just, these decimals convert pretty easily in your head. 19/20ths, again, each 20th is 0.05. This is 0.95, and then this is 1.00. Okay, so now we have cost and more familiar decimal notation, and here we are, right here. Okay, time for a conclusion, and that's that we seem to be able to claim that a minimal cost of 85 cents, can write it like this, is achieved by, okay, now we may have some conversion to do here. Initially we can say, using, now what is this? These are servings, right? 1/2 serving of turkey, and the 2 is the number of servings of cheese. 2 servings cheese, and that implies, what does that mean? Because this isn't fully answering the question. We need to determine how to set that deli slicer, right? Okay, well, let's look back at something we haven't looked for a while. Let's go back to what a serving is here. Okay, one slice was 100 thousandths by 3.5 inches by 3.5 inches. Okay, since we are talking about a half slice, we can reduce that first number, that 100 thousandths, by 1/2, meaning we're looking at a 50 thousandths inch thick turkey slice. In the case of the cheese, it's one serving corresponds to 100 thousandths inch by 3.5 by 3.5 inches. To give ourselves 2 servings, we can just multiply that first dimension, the slice thickness, by 2, and that would bring us to 200 thousandths of an inch there. Okay, this gives us our chance to write our conclusion in the manner it's expected, and so this means we should use a 0.050 inch thick slice of turkey, and 2 servings, that's up to 200 thousandths, 0.200 inches thick slice of cheese. Okay, this is pretty much an important part of the question here. We're at the conclusion phase, so it's time to bring out the rather heavy ink and make the conclusion jump off the paper for someone who just wants to see the bottom line. Okay, bringing us to a conclusion that looks like that. Now, last thing we want to do is, let's give this some sort of check over, because again, if you're solving this, if you were solving this for somebody, a customer, you don't want it to have really absurd errors in it, or something that can be detected by using just kind of common sense. So let's at least get that under control right now. Okay, so here are our check. what we're looking for right now is just sensibility of this, making sure we haven't just gone off by a factor of 10 somewhere and recorded a really nonsensible answer. Okay, so to do that here, what might I do? You know what? Think of going to the grocery store and you buy regular prepackaged turkey, prepackaged cheese. So consider packaged turkey. Okay, when you look at those slices, say you buy the thickly sliced stuff, you have a package. Runs at about, what does it run at? $4, $5, $6, something like that, right? Okay, so let's just say the package is at about $5, and you get 10 slices. About. Okay, and they are at maybe they're 1/16 inch thick. Okay, something like that. So that would mean they're about 62 thousandths of an inch thick. Okay, so this idea means that if we're talking about 50 thousandths inch thick turkey slices, that's okay. That's fine. Means something that's sensible. Also, what about the price of these? If the package is $5, this means one slice has a value of about 50 cents, right? Packaged cheese. What do? You buy some of that pre-sliced sandwich type cheese, and one package is $3, $4, $5, $6, something like that, right? So let's just say it's a package at $5. Okay, you get that kind where it's you get those kind of fairly thick slices, so you get maybe 10 slices. Now cheese slices, those can be kind of thick, so maybe they're a 1/8 inch thick. 1/8 inch, that's about 125 thousandths of an inch. Okay, so our cheese slices here in this question, 200 thousandths. Okay, they're on the thick side, but they're not absurd. And we're looking for absurd things. That's what's going to trigger us to go back and review the whole problem. So this is giving us the clue that our cheese slices here, they're thick, but at least they're sensible. And the price of these things, one slice, if you buy this kind of package, is about at a cost of 50 cents. So the total cost for one slice of turkey, one slice of cheese is about $1. Okay, so both these slices that we're sort of familiar with in our everyday life and the kind of cost that we seem to see at a grocery store, roughly speaking, are in line with what's going on in this question here. So this is all consistent with our claimed solution. What we don't want is to be saying things like, well, we have the minimal cost of $8.50 by doing this, and anybody can come along and say, what? That's just absurd. This is not even close to what is going on in the supermarket. Something must be wrong. Okay, so instead we are in fact consistent with what goes on in a supermarket, and so this answer can at least feel sensible at this point. The next stage of checking, you could consider the details of all of this, quite a bit of manual arithmetic here, right? So there's a lot of chance for some small error here that might have gone undetected and even change the overall conclusion of this. Okay, to do that sort of check, probably the best thing, you have to resolve this question at maybe another day. That's the best thing. So then in case you're making some mistake, you don't make that same mistake a day later. Your mind is clear. You're sort of reset and proceeding on a new path. And that would be a nice way to do a final secondary check on this question. But at least we have something that's pretty sensible here and looks pretty good. Okay.